Roberto Car from Princeton University. Professor Car is a recipient of the Frontiers of Science Award for his work on, maybe I should read this, DP-Zhang, an optimal active learning protocol for constructing interatomic potentials for materials simulation. So now let's welcome Professor Car.
So it works. Okay, so I would like to thank the organizer for inviting me and for giving an award to this paper. This paper, well, let's see, does it work? No, I think I can go this way. And this is a paper that I wrote a few years ago together with 4 other people, Linfeng Zhang, Deye Lin, Han Wang, who is here, and Wenan E, who was my former colleague at Princeton University and now is in Beijing. So in this paper, we introduced an active learning technique for constructing uniformly accurate interatomic potential for material simulation. And the approach that we used is based on 3 steps. One is exploration, the other is generation of accurate reference data, and training. So these are the 3 steps. But in order to place this procedure that we call deep potential generator in the appropriate context, I want to give you some background on molecular simulation, because these potentials are used to do molecular simulation. So molecular simulation, in particular, I'm going to talk about molecular simulation derived from first principles, which mean from quantum mechanics. The basic paper on which molecular simulation relies on is a paper by Born and Oppenheimer that was written almost 100 years ago. Essentially, they realized that due to the difference in the mass of the electron and the mass of the nuclei, the potential energy surface that drives the dynamics of the nuclei can be, there is separation in the dynamics in the electronic and the nuclear dynamics, and the potential energy surface, which is a function of all the coordinates of the atoms, can be obtained by minimizing the electronic energy, which is represented here by minimizing some electronic many-body Hamiltonian with respect to a normalized electronic many-body wave function for a given nuclear configuration. If we can solve this problem, then we can evolve the dynamics of the nuclei, in general, if we are not at too low temperature, by assuming classical mechanics for the motion of the nuclei, and so we solve then numerically a set of Newton's equation for the nuclei. That is the program of molecular dynamics. However, to implement this procedure is impossible even today after 100 years, because solving the many electron ground state problem along molecular dynamics trajectories in materials and molecules is too difficult. So some approximation had to be made, and the important steps are given here. A very important step was the introduction of density functional theory. In density functional theory, instead of minimizing the energy, the expectation value of the electronic Hamiltonian over a many-body wave function, we minimize an energy functional that depends only on the density. That was established, that the ground state is a functional of the density, was established in a paper by Hohenberg and Kohn, and subsequently Kohn and Sham introduced auxiliary single particle wave function in terms of which to represent the density. And if one plugs in that into the functional, of course, the problem with if one plugs into the functional, one obtained that the minimization problem is equivalent to solving a set of self-consistent single particle equation for the orbitals, the Kohn-Sham orbital psi I of R. Well, that is all fine. However, this can be done only approximately because the functional is not known. And in particular, what it is not known is the effect of exchange and correlation among the electron on the functional, and for that one has to adopt some approximate form. So the approach reduces the problem to a single particle problem that has a form similar to the Hartree equation, but while in principle it could be an exact approach, it is in fact approximate because this functional is only known approximately. That had a very important impact, and in fact Walter Kohn got the Nobel Prize in chemistry for this development. And but this approach was still not used for solving the molecular dynamic problem, and because it was too expensive. It was used to solve, for instance, to compute phonons, vibration around a given crystal structure of the atoms, or to compute equation of state as a function for materials, as a function of the energy, as a function of volume or pressure. But still, to do molecular dynamic simulation with that was a little bit too expensive. And that came in with the approach that Michele Parinello and I introduced in 1985, in which we introduced a fictitious dynamical system represented here by a Lagrangian, and from this Lagrangian one can derive equation of motion for the electrons and for the single particle orbitals of Kohn-Sham theory, which allows us to move concurrently electrons and nuclei, we say on the fly, during a molecular dynamics trajectory. So that opened the field to study finite temperature properties of material, to study liquids and disordered material, chemical reaction on the fly, and so on and so forth. But still, it was too expensive for large-scale simulation. Typically, even with today's computer, with this approach, one can study system with up to few to several hundred atoms for time scale of the order of 100 picosecond, but we need to go to larger system, and also to do longer simulation to get sufficient statistical sampling in difficult situation. So here is where the revolution of machine learning came in. Using machine learning and neural network representation, one can represent the potential energy surface that is given by this functional minimum of this Kohn-Sham Oehnberg functional in terms of atomic energies. The sum over I here runs over the atoms or the nuclei in the system, and each atomic potential depend on the coordinate of the atoms that are in its neighborhood, and that can include a substantial number of atoms. So it's a truly many-body potential energy. In order to go to this representation, we used several principles. One is the fact that indeed in many cases the electronic matter is what Walter Kohn was used to say is nearsighted. And so we don't need to include the effect of the boundary very far away. And so this representation is good. And then in order to use this representation, we have to include in the architecture of the neural network the symmetry properties of the system that are translational, rotational, and permutational invariants of the neighborhood. Then, having a proper architecture, we can train the neural network with machine learning on density functional theory data. This is one possible implementation of this formalism is the deep potential model, and that's the reason why we call our scheme for learning deep potential generator, but there are many other neural network model to describe the interatomic interaction. And this deep potential model was developed originally in the thesis work of Lin Fong Zhang, who was advised by Wenan and myself at Princeton a number of years ago. So once we have that, we can do molecular dynamic simulation now for systems that are much larger. There have been examples with million atoms, but if you want really to do understand the physics or the chemistry, you use smaller systems because you have to do a lot of simulation, just not one-shot demonstration that you can do the large system. And one can study, let's say, thousands, hundreds of thousands of atoms or more for time scale of the order of several tenths of nanoseconds. So it is several order of magnitude improvement with respect to the direct ab initio molecular dynamics, and also has a better scaling because these things scale linearly with system size, and the solution of the Kohn-Sham equation scale depending on the algorithm that one uses, scaled cubically or even with a higher power quartically with the system size. So that definitely helps a lot. So this is why machine learning is useful. However, in the machine learning, still relies on the density functional theory calculation, because the parameter of the neural network have to be learned by machine have to be learned by performing by labeling configuration with density functional theory calculation. So that is still expensive, and so that raises the question of optimizing the learning in order to reduce the number of expensive quantum mechanical calculations that are necessary for a given target of accuracy. And that was the content of the paper that has been awarded. And in this work, we were inspired by a paper that appeared in 1992 that is called Query by Committee. In this paper, the author of this paper studied some toy statistical mechanical model, and they imagine a procedure in which a committee of students learn from a teacher by asking a question to the teacher. And they, in particular, they considered what was best, asking question at random instances or asking question when the committee of students had maximal disagreement between them. And they found out that asking question when there is maximal disagreement lead to an exponential rate of learning for the toy statistical model that they studied, while instead using just a random sampling of the data only gave a learning that was that had a polynomial rate, so much slower. So that is the kind of principle that we are going to use, and we developed a scheme to use this principle, combining that with on-the-fly search for the optimal potential. Now, the neural network parameter that are called W here are obtained by minimizing with a stochastic gradient descent procedure the loss function that I have written down here. And in order to apply on the fly a query by committee procedure to this process, what we have to do, we can consider now not the committee of students is now an ensemble of neural networks that are trained with the same data but differ from in the initial conditions. So we have some representative members of this ensemble, and we keep exploring by doing deep potential molecular dynamics, which is cheap, different thermodynamic conditions, and with all these representative members of the ensemble. And when the representative members of the ensemble are in agreement, that's okay. It means that the potential that we have at that point describes well that situation. But when there is disagreement between the prediction by the different members of the ensemble, that is the point when we have to acquire new quantum mechanical data. And the disagreement, the maximal disagreement, is represented here by the maximum deviation within the ensemble of the square deviation of the forces within the ensemble, the maximum spread of the forces within the ensemble. So that does not require any quantum mechanical calculation. But when we have this condition of maximal disagreement is realized, then we have to acquire quantum mechanical calculation. So we do the labeling, and the quantum mechanical data are added to the training set, and this procedure, and so we acquire new data, we have a better potential, and this procedure is repeated iteratively until we have a potential that describes the system uniformly well in a given target region of thermodynamic condition. So that is, in short, the content of the paper. And in the paper, we also presented some comparison of the potential that one could construct in this way relative to a state-of-the-art empirical potential, which for metallic system is the modified embedded atom model. So this is a potential in which the potential of the atom depends on its environment, but in a much simpler way with only few parameters that describe the dependence of the potential on the environment. Instead, in this case, it depends on an environment that is much larger and with many parameters in the neural network. And as one can see, we use in this work, we used this potential to model aluminum and magnesium. In particular, here I present data for the potential in the case of a phonon calculation for aluminum, and you can see there are also experimental data that are represented here by these crosses. You can see that the deep potential reproduces much better the phonon dispersion curves than the modified embedded atom model. Also here we have the pair correlation function of liquid aluminum when the system melts at high temperature. So this is a temperature of above 900 Kelvin. And we can see again that the deep potential reproduces quite well relative to experiment the pair correlation function, while the MAM potential does not. Also, we consider various alloys made by magnesium and aluminum with composition ranging from, what is that here, from 25 to 94% relative concentration. And again, the deep potential is able to represent, here we have the formation energy of the alloy and the equation and the volume, the formation volume of the alloy, and the deep potential is in much closer agreement with experiment, with DFT in this case, than the MAM potential. So, in this case, we explore a vast number of unlabeled configurations, 650 millions, but only a small fraction of those were selected for labeling. Now, okay, so that was to show that this scheme was indeed effective. Now, can we do something new with the scheme? And indeed, that is the case. And one application that we did of this approach was the first prediction of the phase diagram of water over a vast range of temperature and pressure, entirely based on density functional theory, so no free parameter. And you can see here in red are the boundary line that distinguish different ice polymorphs, these 3, 1H, 11, and so on and so forth, correspond to different ice polymorphs. And then there is the fluid phase, the liquid water, and we went up to pressure of the order of up to 50 gigapascals, so a very large pressure. And that description was better than what was achieved before with empirical potential, and particularly empirical potential in this case consider water molecules that are that cannot dissociate. When we are at high pressure, for instance, if we sit at a pressure of 1 gigapascal, which will be here, where is that? Well, this is 10. Yes, you sit a pressure here at 10 gigapascal, and we keep compressing this system, in particular this I7, keep compressing the system becomes superionic, which means that the water molecules start dissociating, and while the oxygen remain in the crystalline position, the hydrogen or the proton start moving around so that the system is a superionic system, and eventually this keeps increasing the number of protons that diffuse in this system until there is a weak first order phase transition. And that weak first order phase transition we could see because we could study the size dependence. We saw a jump in the enthalpy and in the volume, and we could also understand where that was coming on microscopically, because in this system there are two interpenetrating network of hydrogen bond, and the weak first order transition occur when the two network are equally disorder, there is equal disorder in the two networks. That releases a certain cohesion in the system so that the volume expand a little bit. And that is something that we could find in this simulation and is in agreement with experimental data that were obtained just a year before we did that, because it's very difficult also to do this thing experimentally. So that was one application that was made possible by DPGen, because without having the DPGen, we would have not been able to do all the calculations that are necessary to describe this system in this vast range of thermodynamic conditions. I must also say that the agreement with experiment is not perfect, and for instance, the melting temperature of ice is higher than 0 centigrade at standard pressure by about 40 degrees, and that comes because of the inaccuracy. But if you measure in energy units, that is a very small energy, and so that's what it is. Now, this kind of procedure now have been included in an open source software. And for standard thermodynamic target conditions, like the ones that I described so far, essentially the procedure are automatic. So standard, I mean different pressure and temperature in a single phase. And you can do that for one phase, for another phase, and the training procedure are essentially automatic there. However, there are situations in which that need special care and ad hoc procedure. That happens when we deal with rare events. So important events that occur very rarely on the time scale of the dynamic of the molecular dynamic simulation. For instance, a chemical reaction that will not occur, or if we want to study the dynamics of the transition from a metastable state, the nucleation of a stable phase out of metastable equilibrium. In this situation, non-Boltzmann sampling techniques are necessary. Essentially, we have to identify collective variables, or so-called reaction coordinates, that are variables that depend on the configuration of the atoms that describe this process, and this there is no, as yet, no way to define those coordinates automatically. They require physical and chemical intuition, and then one has to sample the potential energy along this reaction coordinate, and in order to do that, one has to use non-Boltzmann sampling techniques. So this is indeed the case, and I want to present here a couple of applications. This is a famous rare event example, is the self-ionization of the water molecule in the liquid that originate the pH, and which is very important in chemistry. And essentially, this is a very rare event because at standard temperature and pressure condition, you have one molecule over a billion that self-ionize. So it will never occur in a simulation, even if we can do a simulation for 100 nanoseconds with, let's say, 1 million molecules, it will not occur. So we have to force this system to, this event to occur. And that is particularly difficult because if we want, so what we can think of to generate this process is to bring one proton from one molecule to another molecule nearby and generate a pair of water, what are called water ions, so hydronium and hydroxide ions because the proton doesn't go freely inside the molecule. They form complexes with the water molecule. One is called the hydronium, that is essentially an oxygen with 3 neighboring protons, and the other is the hydroxide, an oxygen with 1 proton only. So as you can see in this representation here. Now, if we use the distance between the proton and the molecule from which we extract the proton, this won't work because when one creates this defect in the system, the protons are very mobile. They are more mobile. They, on the scale of picosecond scale, on a short time scale on the simulation, they jump from one molecule to the next. And that is called the Grotthuss mechanism, and so we will lose track of the proton. So in order to do that, we used a collective coordinate that was actually suggested by my friend Parinello, which is a global reaction coordinate that is based on a Voronoi tessellation of the system. And so with the Voronoi tessellation for the oxygen in the system, we can identify the oxygen that has 3 protons and the oxygen that has only 1 proton. This is not possible if we use just a spherical shell that define when the proton is here, because there will be overlap between this shell, and so this will be subject to some uncertainty. Well, by using this kind of global reaction coordinate, of course, the Voronoi tessellation will have some discontinuities, but it can be made smoothened out, and the reaction constant for this process can be calculated from standard statistical mechanics. The reaction constant is given by this formula over here, where W is what is called the potential of mean force. So there's the free energy at the coordinate S minus the free energy at infinity when these things are separated at infinite separation. And this integral goes from 0 to the dividing surface between reactant and products in this reaction. By doing this calculation, we can determine what is the value of C, that is when this thing becomes constant, because there is this factor S squared in this integral that represents the entropic contribution, the fact that this object is not just in one direction, but it can have any direction in space. And so even though we have a positive and a negative ion, when they are a sufficiently large separation, their electrostatic attraction is overwhelmed by the entropic factor here, and the ions get free. And that is what happens in this situation, and we could study the convergence with the system size and get a pKw that should be 14, because pKw is equal to twice the pH, and should be 14, but we got a value of 14.7, which is not bad at all, although I must say that this calculation was purely classical, since hydrogens are involved here, and quantum mechanical, there is indeed an isotope effect on the pKw that is more than 1 pKw unit, and that will lower the pKw. So this is one example. The other example that I want to mention is just a recent work, again by my friend Parinello, in which they considered a catalytic reaction at what the chemist called operando conditions. So those are the conditions at which really that takes place, and they they consider this system that is lithium imide and which has a crystalline structure like that. But if we raise the temperature, operandum condition will be at 750 K. At 750 K, the lithium ion, this is superionic, and the lithium ion move around in the system. And so you can see that these are the NH2 minus, that this is a sequence of snapshots over, I don't know, 5 nanoseconds or something like that. And you see that these lithium move around and while the NH2 remain at their situation. So, well, one can see here, yeah, here this is a sequence of snapshot. You see that they occupy all the position in the lattice, whereas the NH2 minus remain close to the crystalline position. Now, what happens is that when they add an ammonia molecule, and they actually add 2 ammonia molecules to the system, the ammonia give rise to the formation of 2 of these imide, and these imide are negatively charged. And so there is a restructuring of the surface that give rise to this sort of soup in which the atoms move around. So this is very dynamic. And with this very dynamic construction, they came out with a catalytic cycle that is can be sustained. That is very important, because in order to have catalysis, you don't have to have just once a reaction, but as you keep providing ammonia, this ammonia should be reduced into nitrogen and hydrogen continuously. And this is one possible cycle that they proposed. So this is a very interesting work. And again, it was possible by using a deep potential construction as the one that I discussed before. And they used DPGen combined with enhanced sampling, again, using a suitably crafted set of reaction coordinates derived from the coordination number of the various chemical species. So that's another application of the approach. I want to conclude with a last one. In this case, the DPGen procedure was used to predict complex crystal structures of dense lithium. And using again, this was based again on DFT and on a deep potential model, and that was used with the procedure that is called Calypso to generate crystal structure. If one uses this Calypso procedure with direct DFT calculation, one can do at most a structure with 20 atoms. But they were able here to consider structure with up to about 200 atoms because of the advantage that they had via the DPGen procedure and the deep potential method. And so this is another prediction of complex crystal structure, is another area that can benefit by this approach. With that, I come to the concluding remarks. Essentially, by optimizing the learning process, DPGen makes possible to construct deep neural network representation of the potential energy surface with an expanded range of validity in a variety of situations, as I have illustrated with this example. In turn, it enhances the reach of ab initio molecular dynamic situation, the molecular dynamic simulation, to situations that could not be studied with standard methods, and accelerate material discovery. Now, the basic principle of DPGen, on-the-fly exploration by an ensemble of network, labeling based on maximal disagreement within the ensemble, and iterative refinement of the deep neural network model are independent of the adopted architecture for the DNN, so that can be used with other deep neural network model, and is also independent of the underlying quantum mechanical model of the potential energy surface. So far, we have to use DFT, which is good but not perfect. It would be good to have more accurate quantum mechanical calculation, but still that is something that require doing quantum mechanical calculation for a reasonably large number of structures, and sufficiently large is not, it is start to be impossible for some special situation. And definitely there will be, I think, development in the coming year in this direction. And with that, I would like to thank you for your attention.
Thank you, Professor Carr. Any questions?
The success of the division scheme in the system with the rare events heavily depends on the design of the collective variables, as
Yes.
the two examples you have shown. As it is heavily handcrafted collective variables. If one wants to develop some more general potential energy surface for category of problems, one has to consider how to design more generalized collective variables to run the division.
Well, yeah, that is an area in which there is work going on. And in principle, one could use what is called the committer ensemble. So you want to go from a state A to a state B, and along the path, you study what is the probability that if you started from A, you will end up in B. This probability will have a sharp change at the transition state. So that defines the transition state. And there is a variational principle due to Kolmogorov that one could use. Again, this is something that Michele has been doing for some simple systems and even not so simple. He seems to be able to get the best reaction coordinate based on Kolmogorov variational principle for the committer ensemble.
Okay.
Yeah.
That's great.
I have a question, which is for the committee voting strategy. I mean, it's a very powerful strategy, but that was also used in the first work, right? So after this many rounds of iterations, are there even more powerful, like adaptive sampling strategies that can be tried?
Oh, well, still, I don't know, maybe you know better, but there are various variations of this strategy, but that is still, I think, one of the most effective used. Can you say something in this respect, Han?
Always gives you a reasonable estimate of the uncertainty of the network approximation. I also use the method based on the variation.
Yeah, that's right.
Estimate the error, but it suffers from the sampling problem to achieve correct estimate of. In some cases, the sampling may be a problem.
So the sampling of the posterior.
Yes.
Yeah. Yeah. Exactly. Yeah.
Thanks for the talk. In the title, you mentioned this is an optimal protocol. May you say more precisely why, in which sense it is optimal?
Well, is largely empirical in the way it is done, in the sense that I described the principle, but now what happens is that when there is this divergence among the prediction of the member of the ensemble, this divergence, when this divergence is above a certain threshold that is fixed empirically based on experimenting with this thing, but then systems are more or less similar in this respect, then you do the label. If it is very far from this threshold, so there is, then it means that it is a completely unphysical situation where, I don't know, atoms sit on top of each other or things like that, and that has to be discarded. And so one has a window of where this spread of the prediction should be considered maximal, a good maximal disagreement, and within this window we select the configuration for new quantum mechanical calculation.
Thanks.
Any other questions? Okay, so if no more questions, let's thank Professor Car again.
Thank you.
And that concludes this
Thank
session.
you.